Okay, I've written a few things in because I really need to point to things or you're not gonna see it. Okay, first of all, I'll leave it to you to establish that this triangle is geometrically similar to this one and that the angle alpha is the same in both. Now, we have our delta S, remember, our displacement along the arc. Okay, and delta S is just equal to A delta theta, where A is the radius of the circle. Okay, remember we used A for the radius. Okay, now this is the magnitude of delta S because it's a delta S without the arrow over it. So it has magnitude of A delta theta. So that delta S parallel, well, it's just the length magnitude of delta S, that's the side of the triangle, times the cosine of alpha. We project this back, and our delta S parallel is going to be delta S cosine alpha. So that delta S parallel is A delta theta cosine alpha. And that's the magnitude of delta S parallel. Now, we're not dealing with the sine of delta S parallel at this point, and that might be a little confusing. But it's easier just to talk about the magnitudes. Okay. Now, A delta theta cosine alpha is the same as A cosine alpha times delta theta, right? And A cosine alpha, if we come down here, this triangle has a hypotenuse of A. Alpha is here, so A cosine alpha is just the magnitude of your Rx. So that the magnitude of delta S parallel is just Rx delta theta. Now, if you think clearly enough about the triangles and what's parallel to what and what's perpendicular to what, you can make a lot of sense out of the fact that the delta S parallel is this times delta theta. Because your delta S is the whole radius times your delta theta. And delta theta, remember, is very small because we're making approximations here. But delta S is just the whole radius times the delta theta. To get delta S parallel, you've got to multiply that by the cosine of theta. So you could just take the A cosine theta and multiply it by delta theta and get the same thing. Think that through. Now, I'm being a little sloppy about signs and magnitudes here, okay? If we get a little more rigorous about it in a way that you can work out if you wish, this Rx is a vector, okay, and this delta S is a vector. Rx is a vector A cosine theta I. Delta S is a vector that makes an angle alpha with Rx. From this, we can see that the magnitude of the work done is what? It's F net times your, well, we started all this out with the idea that the work done was F net times the delta S parallel. So your work is F net times Rx delta theta. Rx delta theta is just your delta S parallel. At least the magnitude is just the delta S parallel. Then we can say that, okay, your work is the product of R net, F net times Rx times your angular displacement. Okay. Now, work is force times displacement if you're in one dimension or in this situation. For rotation, this is your angular displacement, and this F net Rx is what you multiply by your angular displacement to get the work. And in this case, we're going to call this F net times Rx tau, and now we have work, the contribution of the work due to a displacement delta theta, an angular displacement delta theta, is tau times delta theta. Okay? Now, I kind of need to write down the analogy here with the one-dimensional analog that work is the product of force times and displacement, assuming they're both along the same line. Obviously, we know what to do if they're not along the same line. You got to project, get parallel components. Okay. Provided your torque and your direction of motion are properly aligned for a rotating object, you have this. Okay, where delta theta takes the place of delta S, your displacement, and tau takes the place of your force. Okay, so you multiply this tau thing by delta theta, you get the work. Now, more generally, you do this with vectors, and I'm going to get to that here in just a minute. But not everybody's up to the idea of a cross product and so forth. So we're going to go with this analogy to start. Okay, so we call tau torque. So just as work is force times displacement, work is torque times angular displacement. If you go to the angular quantities, you have to use this thing we call torque. And the torque is F net times Rx, okay? Now, in general, and we'll see the definition, and you'll see it in your text, and we'll use it next time by comparison with this. Let's look at what Rx is, okay? Here's your force. Now, a vector from your axis of rotation out to the point where your force is applied, that's called your moment arm. If you take the component of this R vector and let me make sure I'm stating this correctly. Okay, if you take the vector from the axis of rotation to the closest point of the line of application of the force, which would be this point, that's going to be the component of this R vector that you use to calculate the torque, okay? So that your force times Rx just ultimately becomes the force multiplied by essentially the distance from the axis of rotation to the line of the force. Okay, we can see that here, and we'll make a bigger deal of that later. What I want you to see now is that in this case at least, the torque is F net times Rx, and Rx corresponds to a vector from the point of application to the nearest point of the line of action of the force, okay? You don't even have to remember that, it'll come back to you. And then even more rigorously, we can define the vector torque in terms of the net force and the Rx, okay? And that becomes what we call a cross product, and we end up with a torque is your R vector, well, the cross product of your R vector times the net force. So we take this R vector, do what's called a cross product with this net force, and it's equivalent to doing this Rx times the net force, but it also gives us a direction by the right-hand rule. So I'm going to talk about the right-hand rule a little bit, and this is all just background. Next time we're going to dive into just being able to use the analogies that we draw that I'll do on the next board. Okay, so I'm going to come back and talk about the right-hand rule though for just a minute.